Hello students, welcome back to session 11 of linear transformation classes. So in the last class we have studied problems related to Jordan canonical forms. There you have solved the theorem based on Jordan canonical form and also the two problems related to Jordan canonical form. So continuation of this, let us take up another example. Say first I will take up the matrix. So just see this. Show that the matrix A, which has entries like this, is not similar to the matrix B, which has entries like this. Okay, so you need to show this matrix A and B are not similar. For this, what we do is here, so we show that the Jordan canonical form of A is not equal to the Jordan canonical form for B. Therefore, A and B are not similar. First, let us take up the matrix A. Matrix A is this one. So now you consider A square. So you can see that A square is non-zero matrix. Now again you consider A cube. A cube is the zero matrix, which is 0. Means A is a nilpotent matrix of index 3. Okay. Therefore, the Jordan canonical form of A is the standard nilpotent form, which is 0, 1, 0, 0, 0, 1 and 0, 0, 0. Now let us take up the matrix B. So you consider B square, which is non-zero, and again you consider B cube, which is found to be B itself. Means the elements are repeating, means it will not be 0. Means B square is B cube is not B cube is B, which is non-zero, means as this one matrix B is not nilpotent. B is not nilpotent. B is not nilpotent. So you consider the characteristic roots of B now. So this is it is given by mod of B minus lambda I is 0. This implies that 1 minus lambda 1 1 minus 1 minus 1 minus lambda minus 1 1 0 minus lambda, under as a determinant this will be equal to 0. Okay, means this is determinant of B minus lambda I is 0. This implies lambda is 0, 1 and minus 1. Okay. Now we decompose V as the direct sum of V1, V2, V3 such that where V1 is set of all V belongs to V, such that T1 of V is 0, because so for the eigenvalue 0, this is Ti minus lambda I of power of whole power of Li of V is 0. That is the standard that we have studied in the theorem. Here T1 minus T minus 0 of V is equal to 0, means T on V1 gives T1. Directly I have written T1. T1 of V is 0. Second, V2 is set of all V belongs to V such that T minus lambda 2 wholes T minus lambda I power of Li of V is 0, means again T2 minus 1. 1 is the eigenvalue. T2 minus 1 of V is 0. And V3 is set of all V belongs to V such that T3 plus 1, because 1 minus 1 is the eigenvalue. T3 plus 1 of V is 0. Here T1, T2, T3 are the linear transformations induced by T on V1, V2, V3 respectively. Now you see this. T1 of V is 0 means what? T1 is a nilpotent transformation of index 1. And again T2 minus 1 is of V is 0 means T2 minus 1 is a nilpotent matrix, nilpotent transformation of index 1. Similarly, T3 plus 1 is also nilpotent transformation of index 1. Therefore, now T1 is a nilpotent transformation of index 1, means the matrix of T1 is just simply the 1 cross 1 0 matrix 0. And T2 minus 1 is a nilpotent transformation of index 1, and therefore the matrix of T2 minus 1 is M1, say M1, which is 0, but matrix of T2 I need, therefore matrix of T2 is equal to matrix of T2 minus 1 plus 1. So this is matrix of T2 minus 1 plus matrix of 1. So 0 plus 1, this is 1 cross 1 with having entries 1. Okay. Similarly, T3 plus 1 is also nilpotent linear transformation of index 1. Therefore the matrix of T3 plus 1 is M1, which is 0. And therefore the matrix of T3 is matrix of T3 plus 1 minus 1. So this is equal to matrix of T3 plus 1 minus matrix of 1. So matrix of T3 plus 1 is 0, minus 1 is minus 1. So after arranging the subspaces of V according to their dimensions, we get the Jordan canonical form for B, which is given by JB is 1, first one 1 cross 1 matrix with one entry 0 0 0 minus 1 0 0 0 1. This is one block, this is second block, and this is third block J1 J2 J3. Clearly you can see that the Jordan canonical form for A is not same as Jordan canonical form for B. So therefore A and B are not similar. So the given matrices A and B are not similar. Okay. Next let us consider the another topic. So trace and transpose. Okay. Let F be any field and let A be a matrix in Fn, means n cross n matrix with entries in the field F. Okay. Then the trace of A is the sum of elements on the main diagonal of A. Trace of A is the sum of elements on the main diagonal of A. That is, trace is given by A. If A is equal to alpha ij, alpha 1 1, alpha 1 2, extra alpha 1 n, and so on, then trace of A is the elements, sum of elements on the main diagonal, means say alpha 1 1 plus alpha 1 alpha 2 2 plus etc alpha n n. In summation notation, this can be written as summation I is equal to 1 to n alpha I. Okay, this is the trace of a matrix. Now we have the following result. The lemma says if A and B are any to n cross n matrix over a field F and lambda belongs to F, then trace of lambda A is same as lambda into trace of A. Trace of A plus B is same as trace of A plus trace of B, and trace of AB is same as trace of B into A. Okay, here TR denotes the trace of A. Now first one, let A be the matrix with entries Aij. Okay, then trace of A is what? Summation I is equal to 1 to n Aii. Consider lambda into trace of A. Now lambda into trace of A is lambda into trace of A is summation I is equal to 1 to n Aii. So this can be written as summation I is equal to 1 to n lambda times Aii. Surely we can write like this. So this is equal to trace of, this is nothing but trace of lambda times A. Therefore trace of lambda times A is equal to lambda into trace of A. Thus we have proved the first condition. So second one, let us take A is equal to Aij and B is equal to Bij, B any two matrices, n cross n matrices over F. Then trace of A plus B is equal to summation Aii plus Bii. You know this. So this can be written as summation Aii plus summation Bii. So this is nothing but trace of A plus trace of B. Therefore trace of A plus B is same as trace of A plus trace of B. Now let us come to the third one. So third is, let us take A is equal to Aij and B is equal to Bij. Then A into B is definitely gamma ij, the product, where gamma ij is given by summation k is equal to 1 to n Aik into Bkj. This you know by the rule of product of any two matrices. And Ba is delta ij, where delta ij is given by summation k is equal to 1 to n Bik into Akj. Now consider trace of AB. Trace of AB is what? Gamma ij. Therefore summation I is equal to 1 to n. Summation I is equal to 1 to n. So this is the gamma ij is summation k is equal to 1 to n Aik into Bkj. So this is can be written as summation k is equal to 1 to n. Summation I is equal to 1 to n. Interchange the summations. So this can be written as Bki into Aik. Bki into Aik. So this is nothing but summation k is equal to 1 to n delta kk. Delta kk means trace of Ba. So therefore trace of AB is trace of Ba. Trace of AB is same as trace of Ba. So now if A is invertible, suppose the matrix A is invertible, then trace of AC A inverse is same as trace of C. Okay. So for this, let us take B is equal to C into A inverse. Then trace of AC A inverse. Trace of AC A inverse can be written as trace of A into C into A inverse is B. Therefore trace of AB. But trace of AB is same as trace of BA. B you write trace of B. B is C into A inverse into A. A into A inverse is I. Therefore trace of C. Therefore trace of AC A inverse is same as trace of C. Okay. Now look here. If T belongs to A of V, then trace of T is the trace of the matrix of T. Suppose if T belongs to A of V, then trace of the transformation is nothing but the trace of the corresponding matrix of the transformation. Here M of T is the matrix of T in some basis of V. Now look here. This lemma says if T belongs to A of V, then trace of T is the sum of characteristic roots of T. If T belongs to A of V, then trace of T is nothing but the sum of characteristic roots of T. So for this, say let us prove. Suppose the matrix of T is Fn. Suppose the matrix of T is Fn. If Kn is the splitting field for the minimal polynomial of T over F. If Kn is the splitting field means the field where the given polynomial can be factored into linear factors. Where splitting field is nothing but the field where the given polynomial can be factored into linear factors, or where it is the field where the given polynomial has roots. Okay. Then you know that in Kn we can definitely bring T to the Jordan form J. Because T, the condition for Jordan form is the minimal polynomial can be factored into linear polynomials or linear factors. So if we transform the minimal polynomial into linear factors, then definitely it can be bring into Jordan form J. Now, and each characteristic roots of T definitely appears in the main diagonal of J by the Jordan form, you know this. So all the eigenvalues lies on the main diagonal. Thus trace of J is nothing but the sum of characteristic roots of T. But J is AT A inverse, because J is AT A inverse, where A is the invertible matrix. But J is equal to AT A inverse, where A is the invertible matrix. Therefore trace of J is trace of AT A inverse, but trace of AT inverse just now we have shown the trace of T. So trace of T is equal to trace of J, but trace of J is nothing but sum of characteristic roots of T. Therefore trace of T is the sum of characteristic roots of T. Therefore trace of T is nothing but the sum of characteristic roots of T, which is the required thing. Okay. Now let's come to this. Suppose T is a nilpotent linear transformation. Now nilpotent linear transformation has all its eigenvalues zeros, definitely they all lie in a field. Okay. Therefore trace of the nilpotent linear transformation is sum of elements on the main diagonal. They are the eigenvalues, means they are all zeros, means trace of T is 0. Means if T is nilpotent, then trace of T is 0. But we know that if T is nilpotent, then T square, T cube, etc., any power of T, they are all nilpotent, because if T is 0, T square is 0, T cube is 0, T power of K is 0, and so on. Thus trace of T power of I is 0. If T is nilpotent, trace of T power of I is 0, that we have proved in the last class. Thus trace of T power of I is 0 for every I greater than or equal to 1. Means if T is nilpotent, trace of T power of I is 0 for every I greater than or equal to 1. Now can the converse holds true? Can the converse of this result holds true? That is, if trace of T power of I is 0, can you declare that T is nilpotent? If trace of a transformation, trace of T power of I is 0, then is it implies that T is nilpotent? So I am saying, say, is the converse holds true? The answer is no, because look here, if the characteristic field of the field is 2, then the unit matrix in F2, has trace 1 plus 1, that is 2, but in a field of characteristic 2, 2 is 0. Okay, so the unit matrix means 1 0 0 1 in F2 has trace 1 plus 1, which is on the main diagonal, which is 0, but the unit matrix is not nilpotent because you take any power of a unit matrix, it cannot be 0. Therefore, the converse is not true. Now we give a condition under which this converse holds true. Okay. So that is stated in a theorem as, look here, this is a very important theorem. If f is the field of characteristic 0, if f is the field of characteristic 0 and if t belongs to a of v is such that trace of t power of I is 0 for all I greater than or equal to 1, trace of t power of I is 0 for all I greater than or equal to 1, then t is nilpotent. The condition is the field must be of characteristic 0, then only this result holds true. Okay. For this, let us take up the proof. Suppose t belongs to a of v. If t belongs to a of v, then definitely t satisfies some polynomial. Let p of x be the minimal polynomial of t, because every transformation satisfies some polynomial. Okay. Therefore, t satisfies some polynomial. Let p of x be the minimal polynomial of t. So, p of x will be taken as x power of m plus alpha 1 into x power of m minus 1 plus and so on alpha m. This be the minimal polynomial of t. Now, this is a minimal polynomial of t means, according to definition, p of t is 0. P of t is 0 means what? T power of m plus alpha 1 into t power of m minus 1 etc. Alpha m is 0. You take a trace for the above transformations, sum of transformations. This is equal to, this implies trace of above thing will be equal to 0. Now, trace of a plus b is trace of a plus trace of b. Accordingly, the trace is linear operator. So, trace of t power of m plus alpha 1 into trace of t power of m minus 1 etc. Alpha m into trace of 1 remains, trace of 1 is 0. But they were given trace of t power of I is 0 for every I greater than or equal to 1. Accordingly, in the above expression, only alpha m into trace of 1 remains. Now, alpha m into trace of 1 is 0. But if dimension of v is equal to 1, trace of 1 means what? It is the trace of a unit matrix or a identity matrix having order, say, n. Then what is the trace? Trace of unit matrix having n cross n unit matrix means what will happen? That becomes n. Okay. If dimension of v is n, then this becomes alpha m into trace of 1. Alpha m into trace of 1 means trace of I, which is n, because 1 0 0 etc. 0 1 0 etc. up to n means 1 plus 1 up to n times means alpha m into n. Now, alpha m into n is 0, but f is a field of characteristic 0. Therefore, what will happen? Alpha m must be 0 because n cannot be 0, because it is the dimension means it is a positive quantity. So, n cannot be 0, and in a field of characteristic 0, if the product of two elements is 0 means one of them must be 0, means alpha m must be 0. Now, alpha m is the, look here, look at the minimal polynomial. Now, here alpha m is the constant term of the minimal polynomial. If the constant term of the minimal polynomial itself is 0, what you can declare? The transformation is singular transformation, because if the constant term of the minimal polynomial is non-zero, then we have proved that the transformation is regular or non-singular. Here the constant term is 0, therefore we can declare that the transformation T is singular. Singular means what will happen? By the definition, it carries non-zero vector to 0 vector, means it becomes 0 becomes a characteristic root of T. Consequently, because T of V is equal to 0 means T of V is equal to, I can write T of V as, look here, T of V as, T is singular means it carries non-zero vector to 0 vector. T of V is 0. So, means T of V is equal to 0 times of V. 0 times of V means lambda is here 0. Lambda is here 0 means 0 is an eigenvalue. So, for a singular transformation, 0 will be an eigenvalue. One eigenvalue we got it now. So, let us continue the proof. Okay. Now, let us consider T as a matrix in Fn. Let us consider T as a matrix in Fn. And T as a matrix in Fn means therefore T is also a matrix in Kn, where Kn is an extension of F, where K is an extension of F. Okay. Now definitely if we extend f to k, definitely k contains all its characteristic roots of t. All the roots of characteristic roots of t lies in k. Therefore in kn we can bring t to triangular form, because the definition of the criterion for the triangular form says all the eigenvalues must lies in a field. So accordingly yes, t can be bring into triangular form. Now already 0 is a characteristic roots of t. Therefore we can actually bring it to the form 1 eigenvalue lies on the main diagonal 0 and other things I written 0 0 etc. beta 2 alpha 2 etc. 0 beta n. This is star etc. alpha n. Star denotes the part which we are not interested in. We are interested only in the eigenvalues. So other parts we are not interested, that I will written it as star. So this can be written as 0, the other part is 0, the remaining part is star. This is T2. This is the important part. This is what we are going to find it now. Okay, T2. Now T2 is what? Alpha 2, 0, etc. 0, star, etc. alpha n. Okay, what is the order of this matrix? Definitely one eigenvalue 1. This we have taken out, means so among n 1 taken out, so n is an n minus 1 cross n minus 1 matrix. Therefore t power of k, now this is t power of k becomes what? 0 0 star t2 power of k, t2 power of k. But trace of t power of k is 0, but trace of t power of k is nothing but trace of t2 power of k. So therefore trace of t2 power of k is 0. Now T2 is an n minus 1 cross n minus 1 matrix with the property that trace of T2 power of k is 0 for every k greater than or equal to 1. Now use the above same criterion. Now we assume that trace of t power of k is 0 and we arrive at T2 power of k is 0. Now use the same condition, or you make an induction on the dimension which is n. You make an induction on the dimension of v which is n, or you repeat the arguments on T2 used for t. Then we get, since alpha 1, alpha 2 etc. alpha n are the characteristic roots of T2, we find that alpha 2 is 0, alpha 3 is 0 etc. alpha n, they are all zeros. Thus when t is brought to triangular form, all its entries on the main diagonal are 0. Therefore all its entries on the main diagonal are zeros, means we can declare that t is nilpotent. T is a nilpotent, means we have assumed that if f is the field of characteristic 0 such that trace of t power of I is 0, then we have shown that t is a nilpotent linear transformation. Okay, this is one of the important result. Next, let us take up the other simple result. So this result says, this lemma is also known as the Jacobson lemma. The Jacobson lemma says, if characteristic of f is 0 and if s and t are transformations on v or operators on v such that st minus ts, the transformation st minus ts commutes with s. It commutes with s, then st minus ts is also nilpotent. If the characteristic of f is 0 and if s and t are linear operators on v such that st minus ts commutes with s, then st minus ts is also nilpotent. So for this, for any k greater than or equal to 1, you consider st minus ts power of k. Now st minus ts power of k can be written as st minus ts power of k minus 1 into st minus ts. So this is equal to st minus ts power of k minus 1 into st. I made a multiplication, minus st minus t power of k minus 1 into ts. Now st minus ts commutes with s implies what? St minus ts power of k minus 1 into st is same as t into s comes. Therefore it commutes with s means what? This into s is s times this one, means s into st minus ts power of k minus 1 into t. Let b be the transformation st minus ts power of k minus 1 into t. You take this as b. Then the above expression st minus ts power of k becomes s into b minus b into s. This implies trace of st minus ts power of k becomes trace of sb minus bs. So this is equal to trace of sb minus trace of bs, but trace of sb is same as trace of bs, therefore it will be equal to 0. Therefore trace of the transformation st minus ts power of k is 0. Then by the above lemma, what you can declare? If trace of t power of k is 0, then t is nilpotent. Accordingly, st minus ts is nilpotent. Okay, are you understand now? Accordingly, st minus ts is nilpotent. Now let us take up the other example. Okay. So this example says you find the trace of the following operator on R3. The operator is given by t of xyz is equal to a1x plus a2y plus a3z, b1x b2y plus b3z, c1x c2y plus c3z. This is a triplet. Okay, t of xyz is this one. Now we need to find the trace. We need to find the trace means directly you cannot find the trace of the transformation. For this we need to find the trace of, first we need to find the matrix of t in some standard basis, then the trace of t is nothing but trace of the corresponding matrix. So let us calculate the trace of t as using standard basis. What is the standard basis of R3? The standard basis of R3 are 1 0 0 0 1 0 0 0 1. I call it as E1, E2, E3. Definitely we can find that the matrix of the given transformation is found to be as like m of t a1 b1 c1 a2 b2 c2 a3 b3 c3. Therefore trace of t is what? Sum of the elements on the main diagonal. This is a1 plus b2 plus c3. This is the trace of the given transformation. Next example. Let us take this example. Suppose V is the space of all 2 cross 2 matrices. V is the vector space of all 2 cross 2 matrices over the reals. And let M be the matrix with entries 1, 2, 3, 4. I will define an operator T on V by T of A is M times A. T of A is M times A. Then we need to find the trace of this transformation T. Now to find the trace of the transformation, we need to find, as I said, we need to find the matrix of T first. Okay. So matrix of T first in the standard basis. What is the standard basis for the vector space of 2 cross 2 matrices? So the standard basis is 1 0 0 0 E1, E2 is 0 1 0 0, E3 is 0 0 1 0, E4 is 0 0 0 1. So this is the standard basis. So using this standard basis, I calculate the matrix of T. So now T of E1. T of E1 is by definition M times into E1. M times into E1. M is this 1 2 3 4. E1 is 1 0 0 0. So you get like 1 0 3 0. Now 1 0 3 0 can be written as 1 into 1 0 0 0 plus 0 into 0 1 0 0 plus 3 times into 0 0 1 0 plus 0 times into 0 0 0 1. So 1 into E1 plus 0 into E2 plus 3 into E3 plus 0 into E4. This matrix can be written as the linear sum of the basis elements. Similarly, T of E2 can be written as T of E2 is M into E2. M into E2 is you get 0 1 0 3. So this becomes 0 into E1, 1 into E2 plus 0 into E3, 3 into E4. Similarly, T of E3 is M into E3. M into E3 is 2 0 4 0. So 2 into E1 plus 0 into E2 plus 4 into E3 plus 0 into E4. And finally T of E4. T of E4 is what? M into E4. M into E4 is 0 2 0 4. So 0 into E1 plus 2 into E2 plus 0 into E3 plus 4 times E4. Therefore the matrix of T is what? You take the entries. First is So 1 0 3 0. Second is 0 1 0 3. Third one is 2 0 4 0. Fourth one is 0 2 0 4. 0 2 0 4. Therefore, trace of T is trace of the matrix of T, which is nothing but 1 plus 1, 2 plus 4, 6 plus 4, it is 10. Therefore, the trace of the above matrix is, above transformation is 10. Okay, understand this? Next one. So, let us take up the final example of this class. Say, using trace argument, prove that if the characteristic of a field is 0, then it is impossible to find the matrices n cross n matrix A and B such that AB minus BA is 1, or in other words AB is equal to BA. If the characteristic of F is 0, then you prove that we can not find any two matrix A and B such that AB minus BA is 1 or AB is equal to BA. And in second one, in part A, prove in fact that 1 minus AB minus BA cannot be 1 minus AB minus BA cannot be nilpotent. You prove that this cannot be nilpotent. Okay. First A. Suppose they were given characteristic of F is 0. Suppose on the contrary, suppose AB minus BA is 1. If AB minus BA is 1, what will happen? Trace of AB minus BA is equal to trace of 1. But trace of 1 is what? N, because trace of the identity matrix of order n cross n means it is the trace is n. So this implies trace of AB minus trace of BA is equal to trace of 1, which is n, means n is equal to 0. Is it possible? N is equal to 0. Is it possible? This is possible in the field of characteristic n. But we have taken F is the field of characteristic 0, so it is impossible. It is impossible means we cannot find A and B, AB in Fn, means A and B, n cross n matrices A and B such that AB minus BA is equal to 1. So first is proved. Next, again, look here, trace of 1 minus AB minus BA is equal to trace of 1 minus trace of AB minus BA. Trace of 1 is what? N. Trace of AB minus BA is 0. Therefore, n. Trace of 1 minus AB minus BA is equal to n. N means sum of, trace is nothing but the sum of characteristic roots of the matrix. So, this is nothing but sum of characteristic roots of 1 minus AB minus BA. But the nilpotent matrix cannot have the trace n which is non-zero, but because the trace of nilpotent matrix is equal to 0. You know that all the eigenvalues of a nilpotent matrix are zeros, therefore they are lying on the main diagonal, which is 0. Sum is 0, therefore you can declare that 1 minus AB minus BA cannot be nilpotent. Okay. So that's all for this class, and I will continue in the next class. Thank you very much for listening.